Pre-Calculus ACP Blueprint Semester 2, 2017 through 2018. So it's going to be this spring semester of 2018. So these are the official student expectation descriptions for the test you're going to be having in May, I believe. So we're going to go over briefly all these things and work out just a couple problems just to kind of get an overview for what this second semester is going to be like, what we're going to handle. These first three student expectations have to do with parametric equations. And so I'm just going to briefly state here what a parametric equation is. And a lot of real-world uses, like especially in sports and physics. But here's an example of a set of parametric equations. And sometimes we'll call this a parametric equation. What you have is two equations. You have x in terms of t and y in terms of t. And what you're going to do in a lot of these situations is, like this second one here, we're going to convert this parametric equation into rectangular equation, and also vice versa. But this particular one, you have parametric equation, and we're going to do this a couple different ways. One thing that you can do is you can just put the equation, you eliminate a parameter. So t is what we call our parameter, and in the real world that parameter is often time. So what we're going to do is we're going to solve for t and then plug in that solved for t into this y equals equation. So to solve for t here, if we add 3 to both sides of this equation, we have 2t is equal to x plus 3. And to solve for t, we divide by 2. So we have t equals 1/2 x plus, I'll just decimalize it, 1.5. So we can take this and this 1/2 x plus 1.5 and replace it with this t here, and so we're going to have y is equal to this 1/2 x plus 1.5 squared, and we could expand it out. So far we get 1/4 x squared plus, I don't know, I could work it all out. So this is these ones right up here, I'm going to box in, are what we call parametric equations. Okay? And what we did is we converted this into an equation in terms of x and y, which we call rectangular. Okay, next, here we have polar coordinates, and I did forget something. I wanted to do something else with this. We can graph this in a calculator. If we go here and I go to Control I, add graph, and we can go to menu 3, and we can go to 4, parametric. And so we have x equals 2t plus 3, and we have y equals t squared. And then we can adjust the value of t. Here we have t is between 0 and 6.28. I'll just leave that the same and press enter. And so this would be a graphed part of that equation, and if we went up here and we changed the scope of that, if we made it from negative 6.28, we would see more of the curve. I don't know what happened here. Negative 6.28. Okay. Enter. One more time. See, I don't know what's happening here. Okay, looks like it's all there. Enter. And I'm not seeing it. It's somehow escaped. Change back. Yeah, there we go. Maybe this is it. Negative 6.28. Oops. There we go. Now we see the parabola. So this is just the version, parametric equation, rectangular version of parametric equation. Okay. Now we're to 4 and 5. Polar coordinates. So, well, polar equations. Graph polar equations by plotting points in gene technology. What happens is we have r equals 3 cosine 2 theta. And theta is our angle, and this is like r, this is our dependent variable. So our radius is dependent on what the angle is. So 3 cosine 2 theta. And this right here, this theta, is our independent variable. So the radius depends on what the angle is. And I'm just going to graph this in the calculator. So we go Control I, add graph, and we're going to go to menu 3, and we're going to go to polar equation 5. So we're going to say r equals 3 cosine 2, and to get the theta symbol, and to get to the symbols, I think that's where we get it. Yeah, there we are. Press this symbol key over the left, press that, so we have 3 cosine 2 theta, and this is what it looks like. This is called a Rose equation, a Rose panel. So that's the use of technology. It's kind of neat, the patterns we're going to see. Next, 6, 7, and 8, relations and geometric reasoning. Okay, conic sections. In conic sections, we're talking about 4 ones, basically. We're talking about a parabola, a circle, an ellipse, and a hyperbola. And you can kind of see that, let's see, characteristics of a hyperbola. So there we are, 2 questions about hyperbolas. Then ellipse, 2 questions about ellipse, and then 1 question that's going to cover kind of conic sections in general. And in our ACP formula chart, this is the part of our ACP formula chart, and we have this conic sections. So the standard equation for parabolas, circles, ellipses, and hyperbolas. So we'll get a look at those. Again, we can do quite a bit graphing these in the calculator. Next, we have 5 student expectations comprising 8 total questions. This has to do with basic trigonometry. And in polar equations and parametric equations, something we talked about at the very end of last year, we had r cosine theta is equal to x, and r sine theta is equal to y. And we're going to go over that a lot more, but it's just something that we need to know. So basically, the only thing I'm going to talk about here is a reference angle. Okay, what is a reference angle? Well, basically, what you have, and the first one here talks about the unit circle. All right, so if we have a unit circle is a circle that is graphed on a coordinate plane with a radius of 1. So r is equal to 1 in a unit circle, and you basically have here, and you just have an xy coordinate plane, and you have the point here on the right is going to be the point 1 comma 0, and at the top of the circle is going to be 0 comma 1. At the left of the circle is going to be negative 1 comma 0, and at the bottom is going to be 0 comma negative 1. So those are 4 points in a 16-point unit circle, and we're going to learn about finding the sine and cosine, and a reference angle has to do with the shortest angle directly to the x-axis. So if we have an angle on the unit circle like this, it starts here and goes around, and so we could say that theta is this angle here. Yeah, it looks like it's about 120, 130 degrees. Doesn't matter. If we say theta equals 130 degrees, what is our reference angle? Well, our reference angle is the angle that is the shortest or smallest to the x-axis. So if we go straight between this angle and the x-axis, we're going to have alpha, which is reference angle, is equal to 180 degrees minus 130 degrees. So depending on which quadrant you're in, you have different rules, and so we're going to go over those. And they're the first one here, periodic function, the real-world use of sine and cosine functions. These last three, 11, 12, and 13, have to do with finding distance using right angle and not right angle trigonometry. Law of sines and law of cosines is where you don't have right angles. We're going to learn about sine, cosine, and actually it's S-I-N-E, but abbreviated sine. We're going to learn about tangent, how to find those. So a lot to look forward to. And the last thing we're going to talk about here for the ACP blueprint is using vectors. Okay, it talks about magnitude and direction, scalar and periodically. There are different forms, magnitude and direction. There's component form. And here's an example problem. If vector v equals 2 comma 3 and vector u equals 5 comma negative 1, find 2v plus u in component form. You notice that I said 2 comma 3. Well, in vector notation, these brackets signify that you have a vector. And so it's like this vector u is 2 comma 3. So if we go to the right 2 and up 3 and go right here, this would be our vector v. Okay, and it's going to be just an arrow, and it's going to end up here at 2 comma 3. Vector u is going to be 5 negative 1, so 1 2 3 4 5, and down 1, so it'll be right here. So that's going to be 5 comma negative 1. And I wrote these in sort of point notation form, but in vector notation form, they're going to be, for vector v, 2, 3 in angular brackets, and then this vector u is going to be 5, negative 1. And then we're being asked to add 2v plus u. So we can just add these together. So 2v equals 2 times 2, 3, and u is equal to, what is that, 5, negative 1. And if we go to the right and just distribute, we're going to have 2 times 2, which is 4, and then 2 times 3, which is 6. And then we can just go ahead and add this 5, negative 1. I'm kind of running out of space here. And we just add these together. We have 4 plus 5. That's going to be 9. And then we have 6 plus negative 1, which is 5. So this is going to be our vector in component form 2v plus u. So this is just a brief introduction to some of the things that are on our ACP blueprint. We're going to go into a lot more detail. I hope it's going to be some challenge, but some fun too. You're going to see a lot of real-world uses. This thing I mentioned earlier, this r cosine theta equals x, and r sine theta equals y is going to be quite pervasive during this semester. So good luck. This will be an opportunity for you just to get a taste of what we're going this semester. And thanks for viewing.